This is option B, medical physics. Hopefully I'm actually able to do this. I haven't looked at this in a little bit of a while. So this is an X-ray emission spectrum for an X-ray tube with a tungsten target. So X-rays are created by just basically chucking electrons at a chunk of metal, and they emit X-rays as they decelerate into the metal. You do get these funky spikes that are to do with the electron configuration of the metal that it impacts. Yeah, so determine the operating voltage of the X-ray tube. So yeah, we are straight in here with I'm on uncharted territory. So I'm going to use this wavelength here in nanometers, because if you think about it, the shortest possible wavelength that I could get emitted would be where all of the energy of the incoming electron gets turned into X-rays. So I would have the energy equal to HF, which is HC over lambda. So I'll use this wavelength to get the energy of the incoming electrons, and then since we're after an operating voltage, I can divide that by the charge on an electron to get the voltage. So 6.63. So this is as much me thinking about how to do this stuff as trying to explain it. It's been a while. Divided by lambda, careful with the units, 0.025 times 10 to the minus 9. These are in nanometers, of course. So that gets me the energy. Um, 7.96 times 10 to the minus 15 joules. Therefore, PD is equal to that over the charge on an electron. And I've got 49.7 kilovolts. Okay. Drawn the diagram above, the emission spectrum for an X-ray tube operating at lower operating voltage and using a different metal target. So lower voltage means, first things first, less energy in the electrons. So if this is smaller, this number is lower. If this number is lower, this number is larger. Obviously H and C are constants. So this needs to shift that way. So first things first, we're going to start at a higher wavelength. The second thing, that lower voltage is going to mean less energy generally, so the intensity is going to be lower. So we're going to get a similar graph, but kind of shifted, if you like, in this general direction. Yeah. And using a different metal target, and is in bold there. Always look out for the stuff they put in bold. And using a different metal target. So that also means that these spikes are going to be in a different place. So at a different wavelength. So I'm just going to draw some sort of curve, and then I'm just going to add some like random spiky bits here. I think that's probably fine. And then second. Oh gosh, that is shocking, isn't it? Anyway, I think it probably is okay. My goodness. Sorry, I should attempt to. Maybe it would be better if I looked at these in advance. I don't know. When a beam of X-rays passes through bone, the X-rays are absorbed and the beam is attenuated. Thickness of bone needs to reduce the original intensity by 50%, and it's a half thickness. Show that So this is the same thing as, this works in the same way as half-lives, except that we're rather than decreasing increase in intensity over time, we are decreasing intensity over distance moved. This is what we want here, isn't it? Intensity equals initial intensity e to the minus mu x, and there is mu in our equation. So we start from here. I equals I naught e to the minus mu x. That's our starting point. 50%. So 50% implies I equals I naught over 2. Therefore, 1/2. Therefore, if you like, I naught over 2 equals I naught e to the minus mu x. The I naughts are going to cancel. So I've got 1/2 equals e to the minus mu x. Therefore, natural log 1/2 equals minus mu x. To be honest, I'd probably be better flipping that before I do this bit. I'm going to do that, sorry. So e to the minus something is just 1 over e to the something. So I've got 2 equal, I prefer it this way. I know it doesn't make any difference. You can do it with the logs afterwards, but still. So natural log 2 equals mu x. X equals log 2 over mu. That's it. Okay. Beam of X-rays being used to detect a fracture in a bone. The half thickness is 1.4. Calculate the thickness of bone that reduces the intensity to 65% of its original value. So the half thickness is 1.4. So what we'll do, we will use the relationship we've just found that says x half equals log 2 over mu. We'll use that to find mu. I don't like centimeters, so I am going to change that to log 2 over 0.014. I'm going to get a value for mu. First things first. So log 2 over 0.014, 49.5. And then the next thing to say is that I is 0.65 I naught, and that is equal to I naught e to the minus mu x. So those can cancel out of that equation. Let me get rid of that so that it actually is an equation. Yeah, so therefore mu x, or minus mu x if you like, is equal to log 0.65. X is therefore equal to log 0.65 divided by minus 49.5, which equals, sorry, Hit 0.7 times 10 to the minus 3 meters, because I did, I mean, if you kept this all in centimeters, it would be fine. You would just have to be a little bit careful with your units here, because by default, mu should be in meters minus 1. Okay. So 8.7 millimeters seems pretty reasonable. Less than 1.4 centimeters. Explain briefly the role played by radio waves in the process of MRI scans. So the way MRI works, you put stuff in a very strong magnetic field, and the magnetic dipoles in it line up with the field, hitting that with radio waves of the right frequency can flip specific particles. It's hydrogen, isn't it? Is it hydrogen? I think hydrogen atoms. Flips them, and then they flip back, re-emitting. So I just want to put that into words for 2 marks. Radio waves of correct frequency or wavelength cause aligned atoms, well, it's actually the nuclei, isn't it? Aligned nuclei to flip and become anti-aligned. That is, of course, a higher energy state, so they do flip back anti-aligned with background magnetic field. I'm not really sure what I'm talking about. I'm pretty sure that is correct, but I don't know if it's what they're after here. The role play, you know, so without that, I don't know what else you need to say. Without that happening, there is no signal. Nuclei flip back and emit. And emit radio waves, which are detected. I think that's probably it. There's only 2 marks here, so I'm going to stop there. MRI scanner uses radio waves of wavelength 5.9 meters. Calculate the magnetic field needed for the MRI to work effectively. I don't know how to do this. It's been too long. So I am sorely hoping that if I look at the formula sheet, I'm going to see something useful. And that looks useful. F equals 42.6 times 10 to the 6 B. So I'm gonna hope for the best that is the right equation. Frequency is equal to something times magnetic field strength, and we're trying to find B. So frequency equals 42.6 times 10 to the 6 B. Yeah, I'm just kind of hoping that is the right equation. This is going to be pretty awkward if it isn't. And then I can use C equals F lambda and sub in C over lambda for the frequency. And kind of vaguely hope that I get a really, really sensible answer. They do have some pretty intense field strengths. But, you know, if this comes out as 1,000 Tesla or something, I'll know that I have gone horribly wrong. And I've got 1.2 Tesla, 1.19 actually. And that is a strong magnetic field. There's no 2 ways about it, but it's not so far off the chart that it's making me suspicious. So I think I might have got that. Okay. We're investigating kidney function. 2 important properties of any radionuclide used as a tracer. So yeah, important properties. I mean, specifically related to the radioactive properties, I wonder. You know, because one of the first properties that comes to mind is that it must be absorbed by the kidneys. If it isn't absorbed by the kidneys, then you can't use it to investigate kidney function. But I don't know if that's what they're looking for here. I'm going to put it in brackets. In general, I don't think that is a good reason, to be honest, a good property, because what they generally do is they will bind the radioactive iodine to some other chemical that will be absorbed by the kidneys. So they'll use a bit of chemistry to, so they can probably choose whatever they like and get the kidneys to absorb it. So actually, I'm not going to bother saying that. I don't think it's what this question is after. I think it needs to be about the radioactive properties. So if we're using this as a tracer, it must be detectable. The radiation must be detectable outside the body. So it needs to be a gamma emitter. It must emit gamma in order to be detected. Because outside the body, because obviously alpha or beta would simply be absorbed by the kidneys themselves. And that wouldn't get us very far. So it must be a gamma emitter. Other important properties, it's going to have a reasonably short half-life. A short half-life, so the patient is not sort of exposed for a prolonged period of time. Patient isn't radioactive for, you don't want to be radioactive for days. On the flip side of that, half-life needs to be long enough for measurements to be taken. Long enough for scan to be taken or whatever. That's what I'm going for. And all right, doctors concerned about a head injury. They have a choice of the following. Okay, so this is a big question. Look, 5 marks. Choice of the following forms. Evaluate the suitability of all 5 types. All right, so 5 marks, 5 types, 1 mark for each. Is that what we're going for? Let's see how good my memory is. See if I can. So we're looking for a bleed in the brain. I don't believe X-ray can see that. X-rays are used for bones, aren't they? So I don't think that an X-ray would detect a bleed. I think X-rays would go straight through a bleed. Would not be affected by bleed. And so it wouldn't show up. I mean, an X-ray, maybe not the best way to phrase this, but X-rays, they just won't notice the difference between blood and brain. So that it just wouldn't show up is the point I'm trying to make. MRI will show this. So yeah, this is, okay, soft tissue, isn't it? So MRI will show blood and brain, and so it could be used. Suitability, also low risk. I should probably mention about the X-rays. High risk X-ray in brain. It's the last thing you want. Ultrasound doesn't go through bones. So ultrasound, you can't ultrasound someone's head. I don't know what an ultrasound B is. So that's not very useful. But in general, ultrasound isn't any good for the inside of your head. So no good for inside skull. Radioactive tracers could be used arguably. Could they though? Very high risk in brain. And I'm not 100% sure it would be effective either. I'm just trying to think, because normally a radio tracer is designed to be absorbed by a particular body part. So, you know, you could probably make it absorbed by the brain, but it would still be present in the... not sure. Sorry guys, I just I'm a little bit too rusty on this to know if it's even possible to use a radio tracer. Yeah, might not work. Might not show up a bleed. Okay, and CT scan. I mean, a CT scan is basically X-rays, so arguably it's the same thing as an X-ray, it's just lots of X-rays, so it is therefore very high risk, and isn't very good for soft tissue. And I think that's it. Not sure about the radio tracer, so maybe I've only got 4 out of 5 there. Okay, that's it.